21.3 Reversible and Irreversible processes. In this session, we will explore the fundamental differences between reversible and irreversible processes. Our discussion will cover the formal definitions of these terms, the role of equilibrium states, and how they are represented on pressure-volume diagrams, and a specific case study on the adiabatic free expansion of a gas. We will also analyze why real-world processes are inherently irreversible and conclude with a brief introduction to the Carnot engine, which represents a theoretical limit for efficiency. To begin, let us define our terms. A reversible process is an idealization where a system can be returned to its exact initial conditions by following the same path in reverse on a pressure-volume diagram. For a process to be truly reversible, every intermediate point along that path must be an equilibrium state. In contrast, an irreversible process is any process that fails to meet these strict requirements. It is important to note that all natural processes occurring in the world around us are known to be irreversible. We can demonstrate irreversibility using a unique process called adiabatic free expansion. Imagine a gas held in a thermally insulated container. The gas is initially confined to one part of the container by a membrane, while the other part is a vacuum. When the membrane is punctured, the gas expands freely to fill the larger volume. Because the walls are insulating, no heat enters or leaves the system, and because it expands into a vacuum, the gas does not have to push against anything to change its volume. When we perform a thermodynamic analysis of this free expansion, we find several interesting results. First, the work done by the gas is zero, because there is no external force or displacement against the surroundings. Second, the heat transfer is zero, due to the thermal insulation. According to the first law of thermodynamics, if both heat and work are zero, the change in internal energy must also be zero. For an ideal gas, this means the temperature of the gas remains exactly the same after the expansion as it was before. To prove this process is irreversible, we must try to return the gas to its original state without changing the surroundings. If we try to compress the gas back to its original volume, an outside agent must perform work. This work changes the surroundings. Furthermore, compressing the gas increases its temperature. To return the temperature to its initial value, we would need to move energy to an external reservoir. According to the Kelvin-Planck statement of the second law of thermodynamics, this energy cannot be completely converted back into the work used by the engine to reset the system. Therefore, the surroundings are permanently altered. Another way to understand why this expansion is irreversible is by looking at equilibrium. During a sudden expansion, the pressure varies significantly throughout the gas. This means there is no single, well-defined pressure value for the system at any moment between the start and the finish. Consequently, the process cannot be drawn as a continuous line or path on a pressure-volume diagram. We can only plot the initial and final points. Because the intermediate states are not equilibrium states, the process is, by definition, irreversible. When we look at nature, we find that all real processes on Earth are irreversible. We can only approximate a process as reversible if it occurs extremely slowly, which we call a quasi-static process. This keeps the system very near equilibrium at all times. For a process to be truly reversible, it must also be free of non-conservative effects such as friction and turbulence. These effects inevitably transform mechanical energy into internal energy. Since these factors can never be fully eliminated in the real world, true reversibility remains a theoretical ideal. In summary, reversible processes are idealizations that require a continuous path of equilibrium states. Adiabatic free expansion serves as a primary example of irreversibility because it lacks those intermediate equilibrium states and cannot be reversed without leaving a permanent change in the surroundings. Real-world processes are always irreversible because they involve energy losses through friction and turbulence. These concepts lead us to the Carnot engine, a theoretical model used to calculate the maximum possible efficiency a heat engine can achieve using reversible cycles. To conclude, let us reflect on two key questions. First, why is it impossible to represent an adiabatic free expansion as a continuous line on a pressure-volume diagram? Think about the definition of equilibrium and the lack of a single pressure value during the expansions. Second, using the first law of thermodynamics, why does the temperature of an ideal gas remain constant during this specific type of expansion? Consider the values of work and heat transfer in an insulated system expanding into a vacuum.